Welcome. In this video, I'm going to go over the exercises and practice problems from the Brown book pertaining to the first half of Chapter 7, or what I've labeled the 7.1 AB problems. So question 1 says, which statements are correct for a reaction at equilibrium? And statement 1 says the forward and reverse reactions both continue. Yes, that's true. That's one of the definitions for equilibrium. The rates of the forward and reverse reactions are equal. That's also a characteristic of a system at equilibrium. And 3, the concentrations of reactants and products are equal. They can be, but they don't need to be. So this won't always be correct for a system at equilibrium. So only 1 and 2 are correct, which leaves me with answer A. Number 2 says, which statement is always true for a chemical reaction that has reached equilibrium at constant temperature? A says the yield of product is greater than 50%. It can be, but it's not always true. The rate of the reverse reaction is lower than that of the forward reaction. That's never true because then it's not at equilibrium. C, the amounts of reactants and products do not change. That is correct because the forward and reverse reactions are equal, so your concentrations are going to become stable as well. And D, both forward and reverse reactions have stopped. That would be a complete reaction, not a reversible that's at equilibrium. So only C is true out of those statements. Only C is always true for reaction at equilibrium. There, I think I have this figured out. Number 3, which statement is not true for a mixture of ice and water at equilibrium at constant temperature? So this is a physical system, but the same requirements or characteristics are true. Rates of melting and freezing are equal. That's true. That means your forward and reverse reaction are equal. So yes, I would expect that. I grab my pen here instead of my eraser. So yes for A. The amounts of ice and water equal. Don't have to be. They could be, but they're not always. The same position of equilibrium can be reached by cooling water and heating the ice. Yes, you could come from either direction. That's another characteristic. And there's no observable change. Yes, that's true. That's what we call macro changes. Only micro changes would be observable. So B would be my correct answer. Question number 4, write the equilibrium constant expression, so Kc, or what sometimes is called Keq, is always going to be your products over your reactants because product is what we assume we want in any reaction. We typically write the forward reaction to give us the products we're interested in. So for 4A, if I put my products on top, I'm going to have NO2, and it's the concentration. And if there's a coefficient, that's the power. And that is my only product, so that would be it. And on the bottom, it's going to be the concentration of NO squared, because that also has the coefficient. And then it's times, not plus, but times the concentration of O2, and that's just to the first power, so I don't need to bother with an exponent. And that would be my Kc, or Keq, for part A. B, I've got NO2 as my first product to the 4th power times H2O to the 6th power, and that product is going to be divided by NH3. Make sure you include your concentration, brackets, to the 4th times O2 to the 7th. And then C, I've got CH3OH, or methanol, and I've got Cl minus, and that is going to be over CH3Cl times OH minus. So those are the equilibrium expressions asked for in part 4. So I'm going to pause and erase this and move on to number 5. Question 5 wants you to do the opposite. They want you to write the equation given the equilibrium constant expression. And it's really not that difficult because if I look, I see for 5A, I have NO2 squared, so that means my product must be 2NO2. And I've got N2O4 with no exponent given. So this appears to be my equation, and when I look, it's balanced, so I'm pretty confident about that. B, using the same logic, on the product side, I'm going to have CO plus, looks like it's 2H2. No, I guess it's 3H2. And on the reactant side, I'm going to have CH4 plus H2O. And again, it's a balanced equation, so I'm pretty confident about what I've done. Number 6, write the equilibrium constant expression for the following chemical reactions. Well, first I have to know in A that fluorine gas is F2, chlorine is Cl2, and if it forms ClF3, I'm going to need 2 of those to use up both chlorines, which gives me 6 fluorine, so I'd have a 3 here. So now when I write Kc, I'm going to have ClF3 squared over F2 cubed times Cl2 to the first. So that would be 6A. Part B, they're telling you that NO dissociates into its elements, so I've got NO becoming N2 and O2, so I just need a 2 here. So when I go ahead and write this, this equilibrium expression, I'm going to have N2 times O2 over NO to the second. And then part C, methane, CH4, and steam react. Steam's just a form of water, and H2O to form carbon monoxide and hydrogen. So I've got CO plus H2. My carbons and oxygens are okay. It's just my hydrogen. I've got 6 on the one side, so I'm going to need a 3 here to balance things out. So when I go ahead and make my, pull this up just a little further if I can, I go ahead and write my equilibrium expression. I'm going to have Kc equal to CO times H2 to the third divided by CH4 times H2O. Number 7 says, when the following reactions reach equilibrium, does equilibrium mixture contain mostly reactants or mostly products at the specified temperature? Assume that the value for Kc given corresponds to the temperature of the reaction mixture. So A, when I look at it, my Kc value is 7.4 times 10 to the minus 26. So that's way less than 1. And I would get 1 if my product's concentration was equal to my reactant concentration. The fact that I've got a number way smaller than 1 indicates I've got a lot of reactant left. So this one's going to be mostly reactant sitting in there. B, with the same thinking, 2.7 times 10 to the minus 18th, since that's significantly less than 1, that's also going to be mostly reactant. I'm having a little trouble writing here. So these two are both going to be mostly reactant. But C has got a Kc value of 6 times 10 to the 13th, which exceeds 1 by quite a bit. So we can assume this one is mostly product. Number 8, the equilibrium constant for the reaction is 0.0900 at 298. So they're actually giving you a value. They're not giving you the expression for it. And it says, determine whether the following sets of conditions represent an equilibrium mixture. Well, to do this, I'm going to need to know what the equilibrium constant expression is. So that's going to be the concentration of HOCl squared divided by the concentration of H2O times the concentration of Cl2O. So then I'm just going to plug and chug down here. So with A, I'm going to take, so for 8A, I'll just do this down here so you can see. I'm going to take the HOCl concentration, which is 1. I'm going to square it. Then I'm going to go ahead and divide by 0.1 times 0.1. And when I do that, I come up with 100. So that is quite a bit more than the 0.090, which means I've got way more product than I would expect at equilibrium. So it would proceed left toward the reactants. So I maybe started with a lot of product and I'm coming at it from the reverse direction. B, if I do the same thing and I plug in 0.042 and square it and divide by 0.49 times 0.040, I'm going to come up with 0.0900. So this is at equilibrium. So it's not going to proceed either direction. And then for C, 0.083 squared times, or divided by the product of 0.19 times 0.00033. This is going to give me 110. So again, the reaction is proceeding left. I've got more product than I would have at equilibrium. So number 1 on the practice question says, which statement about chemical equilibria implies they are dynamic? A says the position of equilibrium constantly changes. No, that's not true. Equilibrium implies that there's a balance or not changing. The rates of forward and backward reactions change. No, that is also not true. The reactants and products continue to react. Yes, at the same rate. That's what equilibrium is. And D, the concentrations continue to change. No, they don't, because they're reacting at the same rate. So C implies it's at equilibrium, but still reacting. Number 8, which statement is correct for the equilibrium in a closed system at 100 degrees? All the H2O liquid molecules have been converted to H2O. No, not all of them. There's a balance between forward and reverse reactions. The rate of the forward reaction is greater than the rate of the reverse reaction. Nope, and it's not less either. The rates are equal, which is what makes it at equilibrium. The pressure remains constant. That would be true at equilibrium. So yes, the pressure has to remain constant because the amount of gas is going to remain constant, which is what would affect the pressure. So since that amount has remained constant, then D, I would expect the pressure to remain constant. And then finishing up with number 9, deduce the equilibrium constant expression, Kc, for the reaction. So this one's old hat by now. Oops, I guess I'll use my marker instead. And then I've got Kc, and my product is SO3. I need to square it. And then I've got SO2, also squared, times O2. And it says, state and explain the effect of increasing the pressure on the yield of sulfur trioxide. So greater pressure means greater collisions for gases anyway. Liquids and solids not so affected by an increase in pressure or decrease in volume because they're already packed pretty tight. But we'll definitely see a greater collisions for gases. So the question is, do I have any gases? Well, I have 2 moles on the reactant side versus, I'm sorry, I've got 3 moles on the reactant side versus 2 moles on the product side. So this is going to see a greater increase than the products, greater increase in collisions, because it's more crowded to begin with. So if I increase the collisions more on the reactant side, so more reactant collisions, then the effect is going to be more product, more yield. It's important you realize yield and product mean the same thing. Then part C says, state and explain the effect of increasing the temperature on the yield. Well, in this case, you have to look at delta H. It's an exothermic reaction. So if it's exothermic, increasing temperature, you can think of it as 2 ways. You can either think of increasing temperature is like adding product, because heat is a product, it's released. Or you could think of it, it favors the reverse reaction because the reverse reaction is endothermic and wants the heat. So either way, you are going to decrease yield. I can't remember exactly how the question, does it just say state the effect? So you're going to decrease yield. And then part C wants to know about adding a catalyst. And it not only wants to know, it says state the effects of a catalyst on the forward and reverse reactions, the position of equilibrium, and the value of Kc. So the effect of a catalyst on the forward and reverse reaction is the same. So it affects forward and reverse the same. Increases both, makes it easier for both. And the effect on Kc and yield is none, because it does affect them the same. So there'd be no net effect overall.